Okay, the second module for lecture 4 is for Newton's method and the secant method. Now, you may have heard Newton's method sometimes is called Newton-Raphson. Sometimes you may have heard it that way. So again, let's go get an idea about how this works. Here's our function that we're trying to find the root of. So here on the vertical axis is f of x, horizontal axis is x. Here's our function here. The goal is to get the root right here. So the way Newton's methods works is say that you need an initial guess. So say our initial guess is right here. And that initial guess, we're going to mark it as x, and we're going to use a superscript with a 0 here to represent an initial guess. So the value then of f at x 0 is right there. So the way that this method works is you use the derivative of the function or the slope of the function at that initial guess, and you draw a line tangent to it. Should be right here, and that allows you to find the next guess. So the next guess then would be where that tangent line hits the x-axis, which will be right there. So this now allows you then to get your next guess, x1, and you proceed just as by using the guess of x1, which gets you a value of function down here, which then you get a line that gets you, say, x2 would be like right around here, and so forth. And you iterate basically until you get to the root. So mathematically, the way this looks like, that if you draw this line, you then are getting the derivative of the function f prime of x, and it looks like this. So f of x at 1 minus f of x at iteration 0 divided by the value of x at 1 minus the value of x at iteration 0. So again, this 0 here, this is your iteration number. And then the idea is that ideally, this is 0. In actuality, it does not, as you can see from the diagram. But it should get you a lot closer to the root. But we have our function here, and then so what you can do is rearrange it. So we say then that x at 1 then is equal to x at 0 minus f at x 0 over f prime of x at 0. So it's just a mathematical rearrangement of this function, of this equation up here, solving for x and 1. So if you want to generalize it for any iteration, say n plus 1, say x at n plus 1 then is equal to x at n minus f of x at n divided by f prime of x at n. Okay. So I'll box this here. This is the general equation here for Newton's method. So we can talk about Newton's method with some advantages and disadvantages. So the advantages is that when you compare it to the bisection method, it's a lot faster. But the big disadvantage is its stability. So what do we mean by that? If it's unstable, it means that your selection of an initial guess can really dictate how quickly it converges, or even if it has the ability to converge at all. So say, hypothetically, I'll choose a different color here. Hypothetically, say your initial guess is down here. Well, that line that's tangent to it is pretty much parallel to the x-axis. And if that's the case, then you're not going to get anywhere near the root. You may even diverge at that point. You won't be able to find the root at all. So as long as you have a good initial guess, you converges very quickly. But if you don't, then it could be very unstable, or you may have a lot of problems finding that root. So that's Newton's method. Now, the big thing about Newton's method that dictates how effective it is this derivative right here, f prime of x at n. So how do we handle that derivative? Well, there's three ways. The ideal way is you can just take it theoretically. So in other words, you know the equation, and you're able to take to use calculus to get the derivative of it, and then you just use that to determine what f prime of x of n is. So that's one. The second is you estimate it. So to estimate, we did this in lecture 3, one of the in-class exercises for lecture 3. But the idea here is that f prime of x, should I take it back? I think it's lecture 2 we did this. F prime of x is that f of x plus delta x minus f at x divided by delta x, where delta x is some small number. Another way you could modify this is if you define delta x as epsilon times x, you could say f times 1 plus epsilon x minus f at x over epsilon times x. Either way is fine. The idea here is that delta x is a small number, or you can say epsilon here is a small number. And in the case of here, you would just say simply that delta x equals epsilon times x. So either way is perfectly fine. So those are two ways, but there is a third way. That third way is, I think, pretty clever, because what it does is eliminate the having to deal with it at all, and that is we're essentially going to remove it. And the way you remove it is you use the history of your previous choices. And we're going to call this the secant method. The idea here is that f prime of x at iteration n is roughly equal then to f evaluated at x at n minus f evaluated at x at n minus 1 over x at n minus x iteration n minus 1. So all we're going to do is we're going to substitute f prime of x of n into the equation right here in Newton's method, and we get a new equation that we'll use. So with Newton's method again, it's x at n plus 1 is x at n minus f of x at n. Go back up here. We've substituted in for the x prime, or f prime of x at n, so what we get here is x of n minus x of at n minus 1. And divide the whole thing by f of x at n minus the function of x at n minus 1. So this is the secant method. So a couple notes about the secant method. The first note is now you have a situation where your function, and we'll say that the implementation of the secant method, we'll say is a function g. And the goal is to get for each iteration. So you have x of n plus 1, whereas with the Newton's method it only depended on x of n. It only depended on that nth iteration. Whereas for the secant method you need the value of x at n as well as the value of n minus 1. So you have to store an additional layer of history, if you will. So in other words, often in the code you could say that this is, maybe you can call this x new, x current, and this would be x old. So just like in the lecture 3 in-class exercise where you had to do a calculation, you had to store a value of new, current, and old, you would do the same thing here. And then of course as you go through the while loop you would update it. So that's one. And then the other thing that I'll mention with the secant method is whereas Newton's method you start with a single initial guess, and that a single initial guess is x0. The secant method, instead, because you need a value of x at n and x at n minus 1, you need to start with the bounds. So we're going to start with a and b, just like you would in the bisection method. And these are your first two starting values. So a equals x at 0, b equals x at 1. And so that's it. So you basically start with a at x at 0. You calculate what that value of f at x at 0 is. Actually, that would be right here to fill in the x n minus 1 slot. B, you'd put in the value here. And then from all this, you'll be able to get your first calculated iteration here at x n plus 1. So I'll write it out. So here you'd say that x at 2 would be x at 1 minus f of x at 1 times x at 1 minus x at 0, all divided by the value of function of x at 1 minus f of x at 0. So again, what you're putting in here is, for 1, you're saying that this is equal to b minus f at b times b minus a divided by f at b minus f at a. And that is it.